Test coach. Test. Hello. Test. ठीक है.
Hello. Check. Hello. Hello. Hello.
Good evening, everybody. Thank you. I'm Shumok Rai Chaudhary, and welcome to Ayuka for one of our evening talks. We normally wind down our evening talks in the summer because of the vacation. A lot of people go away, students go away, but it's magic, right? I mean, just look, a good talk, a good speaker, good topic, and we do have quite a lot of eager people. Thank you very much for coming, braving the over 40 degrees Pune temperature outside. I'm sorry about the state of the air conditioning in the auditorium. It's failing. Today it's running at half capacity, and I hope it doesn't get any worse than this. I hope you're comfortable. It's my great pleasure to welcome Puragra Raja Thakurta. Everybody knows him as Raja. Sometimes he fishes out his official name when people get a little puzzled. For me, it's a very special thing because, of course, I've known him for a very long time. We've worked together. It's a brief time when we were even in the same class in Calcutta University. Raja did his degree in physics from St. Xavier's College in Calcutta. Then, after a brief stint at Calcutta University, moved to Princeton University to do his PhD in the era when a lot of great things were happening just before the Hubble Space Telescope was launched, which played a great role in the work he did, early work he did. At Princeton, he worked with some really important people, including Tony Tyson, who was responsible for building some of the earliest digital cameras as part of AT&T. Raja also got the opportunity of doing some early observations, and he'll talk about with the digital medium. Raja then moved on to being a postdoctoral fellow at the Institute of Advanced Study in Princeton, which is around the time I also worked in the US at that time, and we did quite a lot of work together. And then, since then, spending quite a lot of time in Princeton, he's been on the faculty at the University of California at Santa Cruz, which is also coupled with the Lick Observatory. Now, the UCSC plays now a very important role in various future projects as well. And as you know, Ayuka is one of the major players in building the 30-meter telescope, and so is, for example, the University of California, and Raja and his colleagues are also part of that whole big project. And so there are many ways in which the work of their group and their work connects with the work that is done here. So welcome. It's a very broadband topic Raja has, and I hope we'll have some time left for questions and answers before people get so hot they want to go home. Raja Thakurta.
Can you hear me okay in the back, everyone? Thank you. Shumok, thank you for the kind introduction. Our professional careers have been intertwined like that symbol on the podium. They have. There's no beginning or end. Now, Shumok and I have had the pleasure of knowing each other, working together for the better part of 3 decades. And so it's a real pleasure to be speaking here at Ayuka. There's another bit of significance that Ayuka holds in my heart, and that is because one of the books I read when I was a college student, when I was a student of physics at St. Xavier's College, one of the books I read that really steered me towards astronomy and astrophysics was a book written by Jayant Narlikar. It was a book called Introduction to Cosmology. And it was such a beautifully written, approachable book, beautiful balance between technical rigor that a physics college student could appreciate and the wonderfully large questions of of astrophysics and cosmology. So you see I have many connections to Ayuka. This is not only is this my nth visit here, but there are these two very specific connections to, for me, scientifically, to my trajectory as an astronomer. So I am going to cover a range of topics. Actually, I haven't written down all the topics I'll cover. I'm going to talk about galaxies, dark matter. I'm going to talk about how life on Earth is connected to these two things. I will also mention cannibalism, not of humans, but of galaxies, which is related to dark matter, of course. I'll talk about island universes, talk about black holes a little bit. With the latest black hole results, it would be a shame not to talk about them. So, if you're interested, I will be happy to chat with you about how young people, as young as school students, class 9, 10, 11, and 12, have been involved in doing some of the research that I'll present to you today. So it's not just the work of old graybeards like myself, but it's really the work of a lot of young people whose results you'll see here. All right. So I've been on the UC Santa Cruz faculty for a quarter of a century, and 4 years ago I had the pleasure of spending 1 year, a better part of a year, at Google's headquarters in Mountain View. And the reason I want to mention them here is because they helped me build this program for high school students that has really taken off in the last few years. All right. You might be wondering why I'm talking about galaxies. That sounds oddly specific because there are stars, there are planets that could be much more interesting to you. I will try to argue that galaxies are, in a sense, a very basic component of the universe. To do this, I'm going to use an SAT-like analogy. If atoms are the basic building blocks of matter, galaxies are the basic building blocks of the cosmos. And the reason I'm saying atoms are basic building blocks of matter is because it's with the understanding of, in order to understand atoms, the theory of quantum mechanics was developed and really represented one of the biggest leaps in physics. Understanding atoms became synonymous with understanding the quantum nature of microscopic particles. It's a big leap in physics, really. There are smaller particles than atoms. They're clearly electrons and neutrons and protons and quarks, and they're clearly bigger building blocks. There are molecules and there are the concrete blocks that make up this building. There are clearly bigger building blocks. There are planets, stars, galaxies. There are bigger building blocks in matter, certainly. And similarly, when it comes to galaxies, there are smaller building blocks. There are stars, planets, but there are also clusters of galaxies and superclusters. But galaxies are important because if it weren't for the fact that you and I reside in a large galaxy, not just any old galaxy, a massive, large galaxy, the Milky Way, if it weren't for that, we wouldn't have complex life here on Earth. You would be made largely of hydrogen and helium, so would I. None of this equipment would be here. The lecture would be much less interesting. I wouldn't have as good a story to tell if I could speak at all. So let me not have you accept this as fact. Let me provide a little logical chain for why it took the development within a large galaxy to have complex life here on Earth. So I'm going to talk a little bit about our place in the cosmos. And when I say our place, you could imagine your own picture there, picture of a loved one. I'm going to show you a picture of my son. And Shomuk, you didn't know I have a son, but here he is. So this story applies just as well to non-humans. It applies to canines, felines. It applies to the simplest virus and bacteria. It also applies to the most complex mammal. And what is common to them is common to us, is we are all made up complex molecules. Teenagers in this audience are made up of particularly complex molecules, but that's not the kind of complexity I'm talking about. So the molecules I'm talking about are proteins, nucleic acids, and you see a representation here of a protein molecule. Every colored sphere there represents an atom, and it takes atoms that are deep into the periodic table, not right at the beginning, in order to form molecules like these. What I mean by that is hydrogen, the first atom in the periodic table, has one electron with which to form a chemical bond. It is a one-armed atom. It can form one bond, so it can be the end of various branches of this molecule. It cannot be at the center. It cannot be an integral branch point. Helium has two electrons, but it doesn't like to hold hands at all. It's an inert atom. So it takes getting up to lithium, beryllium, boron, and carbon, in fact, with 6 electrons, nitrogen with 7, oxygen with 8. These atoms are very important. Not just those, but the elements that are deeper into the periodic table as well. So when people talk about carbon-based life, carbon is not incidental to complex life. I would say it's integral to complex life, because it's the complexity of these molecules that's at the heart of the complexity, richness, and diversity of life on Earth. A simple molecule can only orient itself in a few different ways, and it would really be a very different kind of life form if we lived with just the first few elements of the periodic table. All right, so in order to understand life on Earth, we have to understand complex molecules, which means we have to understand elements like carbon, nitrogen, and oxygen. They're very common here on Earth, CN and OR. I know you're still breathing, although with at this rate of heat that may stop. But as long as you're breathing, you're taking in nitrogen and oxygen. There's a lot of that in this room. And there's carbon. If you're wearing a diamond ring, I'm not, but if you are, you're carrying carbon on your body. So these elements are common here on Earth. So it's natural to ask whether our parent star, the sun, which we know is undergoing fusion reactions, whether it produced these kind of large, complex atoms. And we know for certain that the answer to this question is no. The sun is undergoing fusion, but it is only converting hydrogen to helium. That's what it's been doing for the last 4.5 billion years. It's not producing any CN and O, any net CN and O right now. And it won't for another 5 billion years. So the sun is a very slow and boring cook. It has one recipe. It can make helium from hydrogen. In fact, the element helium was discovered in the sun. It draws its name from the Greek word for the sun. Now, so if the sun didn't produce these elements, what did? So yes, the answer to that question is no. In fact, these atoms we are talking about are part of our inheritance. We were born, we meaning the sun and earth were born with these wonderful elements. Now, if you're thinking like a scientist, it's not a satisfactory answer to say, I was born with these riches. You want to find out, where these riches came from. How did your ancestors gather these riches? So we should look to our ancestors, the sun's ancestors. The sun's ancestors are stars that lived and died before the sun and earth came to be, before they were born. This is a picture of a star field in the Milky Way. And some of the sun's ancestors looked like the reddish-yellow stars in this picture. Some looked like the bluish-white stars in this picture. The reddish-yellow stars, the yellow stars are like the sun in temperature. The red or orange stars are much cooler, only in a temperature sense. The sun, after all, is the coolest star in the whole universe. But I mean, in a temperature sense, the orange and red stars are much lower temperature. But the bluish-white stars are the really hot stars. Their surface temperatures are in excess of 20, 30, even 40,000 Kelvin compared to the sun's surface temperature of just under 6,000 Kelvin. So these bluish-white stars are very hot. They're hot because they're massive. And then their very intense gravity squeezes the star hard, creates very intense conditions at its center, creates a very vigorous set of nuclear fusion reactions that hold the star up against its own gravity. So everything happens faster in these more massive, hot stars. While the sun is going to convert hydrogen to helium for 10 billion years, these stars, the most massive of them, live for 10 million years, or less than 10 million years. That seems like a long time in a human lifetime, but that's 1,000th the age of the universe. So you can have many generations of these stars between the time the universe started and the sun and earth were formed. So these massive stars are more versatile cooks than the sun because they go through the first 26 elements of the periodic table during their lifetime. So they produce everything up to Fe, iron, 26th element in the periodic table. Up to that, nuclear fusion reactions are exothermic, so they're energetically favorable. Fusion produces energy, and the star can survive that way. So these massive stars are more versatile cooks, they're more rapid cooks, and very importantly, they're very generous cooks. At the end of their lives, they explode. This is a picture of an exploded star as it looks about 1,000 years after the explosion. And what this does is two things. It takes everything that was cooked inside the star and disperses it through the surroundings. Moreover, during an explosion, there's a lot of energy available, so the system doesn't care, endothermic or exothermic. It goes ahead with these reactions anyway. There's so much energy available. And in particular, what happens is neutrons are present in great abundance. These neutrons start bombarding the existing atoms that were, existing nuclei that were produced during the lifetime of the star. When a neutron is captured by a nucleus, it goes up in atomic mass, not in atomic number, it goes up in atomic mass, and then as beta decay happens, it goes up in atomic number, not in atomic mass. So if you make a plot of atomic mass on one axis, atomic number on the other axis, neutron bombardment leads to these steps marching up that chart. You get above iron in the periodic table, and arguably these processes in massive stars, in the lives and explosive deaths of massive stars, can account for everything in our periodic table. Now, that's all fine, but it means we had to be around these massive stars, and a family of stars is what you call a galaxy. Now, this is a picture of a galaxy, and what happens in a galaxy is these massive, the massive stars that explode, their explosion is very, very energetic. The material is moving outward at very high speed. So unless you have a very large and massive galaxy, its gravitational potential is not going to be strong enough to retain the results of the explosion of massive stars. We can see already that if you look at low mass galaxies, galaxies that are 1,000th the mass of the Milky Way or Andromeda, the chemical composition of such galaxies is very different from our own. They are much more chemically anemic than the sun and other stars in the Milky Way. So this is not just conjecture. You can directly see that low mass galaxies are much less chemically enriched than a massive galaxy like the Milky Way. So really, trace our story to understand complex life on Earth. We needed to be part of a large family of stars, a massive family of stars. We needed that dark matter. Without that dark matter, we would have a very different chemistry. Now, I've been talking about this as our family of stars. This is not our family of stars. This is the Andromeda Galaxy. This is a picture that Shomak and I took many years ago. We took this together. But this picture I'm showing because we can't take pictures like this of the Milky Way. We don't have a long enough selfie stick. So I'm showing you a picture of Andromeda, and I'll give you a few stats about this galaxy, but they apply to the Milky Way just as well. So first of all, this rectangle, Shomak and I thought we had imaged all of Andromeda. Turns out we hadn't. Andromeda keeps going beyond this, but this part of Andromeda, the central part, is 100,000 light years across. Light takes a second to travel from the sun to the Earth, 500 seconds to travel from the sun to the Earth, about 4 hours to travel from the sun to Pluto, 4 years to travel from the sun to the next nearest star, but 100,000 years to get across this picture. Okay? And that's one stat. The second thing is a galaxy like this contains about 100 billion stars, one with 11 zeros after it. And it's not the mass of the stars, but it's the mass of dark matter that really holds it together. Now, if this were the Milky Way, we don't live in downtown Milky Way, and we don't live out in the villages. We live somewhere between the center and the edge. We live about 25,000 light years from the center of the Milky Way. Again, if this were the Milky Way, that's where we would be. We would be smaller than a single pixel on this projector, because our solar system is only a light day in size, whereas this is 100,000 light years across. Now, we can take pictures of the Milky Way. They just don't look this pretty. So here we go. Here's a picture of the Milky Way. This was taken by a physics teacher, John Rockman. He lives in Palo Alto, but took this picture from a game park in Africa. This is a time-lapse movie of the Milky Way. And just so you can appreciate the movie, I'm going to remove the labels, and I'm going to play the movie. And you'll see that as the movie plays, the sky gets darker. He started this movie close to a little after sunset. The sky gets much darker. You can see the band of light and clouds, that's the Milky Way. And this apparent rotation of the Milky Way, it's an apparent rotation because this is not news to you. We live on a planet that spins every 24 hours. And in fact, from the angle by which the Milky Way changes during this movie, you can tell that the picture was a little less than 6 hours in duration. It should go from horizontal to vertical in 6 hours, upside down in 12, and then all the way back in 24. So this is something like a 4.5-hour movie. I'll play this one more time. You'll see the trees fluttering, you'll see clouds, shooting stars, lightning, all kinds of things that are in the foreground of the Milky Way. But you see the majestic Milky Way, our home, the very thing that's responsible for our complex life, sweep by. And this is an internal view of the Milky Way. It's like trying to see your nose with your own eyes without the aid of a mirror. So we have a distorted view of our own galaxy. Now, because of this, because we've had this internal perspective of the Milky Way and external perspectives of other galaxies, it really confused astronomers for a long time. Were those things that looked like nebulae, things like Andromeda and other galaxies, were they like the galactic home we had? This was an open question for a long time. And one of the people who was at the heart of this question was not even a scientist, because back then, these kinds of questions weren't within the realm of science. They were within the realm of philosophy. This person is Immanuel Kant, and about 250 years ago, he pondered the question, what is the nature of island universes? What he referred to as island universes could well be thought of as galaxies today. This is a selfie he posted in 1755, and there's a quote from him. It's remarkable that he lived for 80 years. He lived in a small town in what was then Prussia, and he never left his hometown, as far as I know it. And yet he had this truly global perspective, had this understanding of the entire universe for a person who had never left a small town his whole life. So when Kant was credited with the term island universes, he would quickly deflect credit and instead give credit to two English astronomers before him. But most people, 250 years after his death, most people credit Kant with the term island universes. Now, it's sort of a travesty that the university in Königsberg, Prussia, where he grew up, turned him down the first time he applied for a faculty position. It's sort of travesty, right? I bet you've never heard of anyone else from Königsberg, Prussia. I was once giving this talk, and there was a person in the audience who was born in that town. That's the only other person I've ever met from that town. Okay? I've never met Kant, of course, but the only person I've ever heard of from there. So, the university in his hometown turned down his application for a faculty position in the philosophy department. This is very sad because people like Shomuk and I have gotten faculty positions in our universities, and you wonder, what does it take to get a faculty position? Universities have to put together some money, startup package, so they can buy you expensive telescopes. If you're an astronomer, they buy you lab equipment. If you're a physicist, biologist, chemist. If you're a theoretical physicist, your lab equipment looks like a desk, a chair, notepad, pencil, eraser, wastebasket. If you're a philosopher, you don't need the wastebasket. That's the beautiful thing about it. Okay, so Kant ultimately got this faculty position, but his work was forgotten. His work was forgotten for 150 years until a person by the name of Karl Schwarzschild, whose picture you see here on the cover of Time magazine. Astronomers rarely make it onto the cover of Time magazine. Karl Schwarzschild did. He rejuvenated the use of the term island universes, and there was this amazing debate between Curtis and Shapley about the nature of island universes. Shapley, I believe, argued that the island universes were different from the Milky Way we live in. Curtis argued that they were identical to the Milky Way we lived in. So the person who came out the loser in the debate ended up on the cover of Time magazine. This was a mistake that Time made. They were not going to put another astronomer's picture on Time magazine, so instead, a few months later, they put up this picture. This was a much more common Time magazine picture. You'll notice that her name is Jean Harlow. Harlow is his first name. This was Time magazine making a play on words and poking fun at their own mistake, because inside the magazine, they go as far as referring to her as the shapely Harlow, which is a direct dig at Karl Schwarzschild. Okay. She had nothing to do with astronomy, as far as I know. Okay. So, I'm going to say a little bit more about island universes, but I want to take you back to a moment in the fall of 1992, when Bill Clinton was campaigning to become President of the United States. On a cold mountaintop south of Tucson, Shomuk and I were shivering. It was cold, it was October, early November even. And there was no heating inside this dome, right? So if you're worried about the heat, just think about it, a time like that. We were shivering so much that we couldn't type commands on our computers. So we braved it out for a few nights, and we started taking pictures of the Andromeda Galaxy. We took a total of 57 pictures, some in blue light, some in infrared light, and we stitched together what was to be the first digital image mosaic of the Andromeda Galaxy. You're seeing it right here. It's the same image shown 4 times at different contrast levels. And you begin to see what I mean when I say Andromeda doesn't end at the edge of that rectangle. And we started to worry about what this light was over here, or what that little streak of blue was near the top. Started to worry about those. At low contrast, you don't see any of that. You see a little galaxy to the upper right, at sort of 2 o'clock. You see, 1 o'clock. You see that galaxy again. It gets engulfed by the time you go to high contrast, and a different galaxy starts appearing at 9 o'clock on the left of center. Yeah, I could point to it, thank you. So this is M32, this is NGC 205, and one of the things we used this image to study was the process through which Andromeda is ripping those galaxies apart and shredding them, stealing their stars. So you can, yes, astronomers call them M32 and NGC 205. They're wonderfully romantic names. This is how astronomers name galaxies all the time. But you can also think of them as breakfast and lunch, because that's what they are to Andromeda. Andromeda is in the process of eating them. So again, this image was stitched together. I have to give credit to Andreas Berlind, who was an undergraduate at Princeton at the time, Phil Choi, who was a grad student at UC Santa Cruz, and Shomuk and I took the original images. They did the hard work of stitching different pieces together. It's not easy to stitch this together. Fast forward a few years, and here's another image of Andromeda taken more recently. Andromeda hasn't changed during that time. Our equipment has gotten better. So Robert Gendler, who's a doctor in Connecticut, in his spare time, doctors have a lot of spare time, late at night, he takes pictures like this, beautiful pictures. So again, you see the 2 galaxies, different orientation this time. M32 is at 5 o'clock, and NGC 205 is at 12 o'clock. My students and I, over the years, have been using a different telescope, not the one in Tucson, a telescope in Hawaii, to dissect this galaxy in detail, study individual stars. So we can study stars that are well beyond this rectangle and see if they belong to Andromeda. Are they moving like Andromeda? Are they at the same distance as Andromeda? What are the reasons to believe they're part of Andromeda? So we've been studying these stars for a long time. And in 2005, we made a discovery that Andromeda is 5 times bigger than I showed you initially in that rectangle. We stopped with that rectangle because that's how big people said Andromeda was. They said it's 100,000 light years across, or in kiloparsecs, whatever that is. We found that it's 500,000 light years in diameter, and it extends in all directions. So it has this halo around it that's 500,000 light years in diameter. So it's like waking up one morning and finding out you're 5 times bigger than you thought you were. Okay? You're going to bump into things in your bedroom. It'll be hard leaving your bedroom. You're going to bump into things all the time, and I'm going to talk about bumping into things in just a bit. So this is spectroscopy that we've done, taking spectra of individual stars with the Keck 2 telescope. The Keck 2 telescope is a 10-meter telescope. So the mirror of that telescope, the diameter of the mirror would be comparable to the width of this stage, the segmented mirror. It's a very expensive telescope. So we've carefully put it on top of a volcano in Hawaii. Now, another telescope that we as a team have used to study Andromeda is the Hubble Space Telescope. You'll see the word Hubble in the acronym FAT there. We used Hubble for 828 orbits of Hubble around the Earth. Hubble takes 90 minutes to go around the Earth. For about 1 hour out of those 90 minutes, you can train it on an astronomical object. So we spent in excess of 800 hours pointing the Hubble telescopes, different cameras, ultraviolet, visible light, infrared light, at that segment of the Andromeda Galaxy. 6 filters, so 6 colors of light, UV, ultraviolet, optical, and near IR. And now we have a mosaic of 3,000 images, not the 57 image mosaic that Shomuk and I put together, but a 3,000 image mosaic. This is the largest digital mosaic of Hubble images ever made. So I'm going to show you some details of that image. I did want to show you that the full moon to scale, to angular scale, looks like that. So Andromeda is large in the sky. The fact that you can't see it is not because it's small. The fact that you can't see it with your unaided eye is because the night sky is bright and Andromeda is a very small fraction of that brightness, especially its outskirts. So in a high contrast image like this, you can see it, but certainly our eye with its logarithmic response is unable to see anything but the very center. So that's the full moon to scale. So fasten your seat belts, because what we're going to do is zoom in to a segment of the Hubble image mosaic. So I'm going to start by zooming out. So that arc of gas and dust is the arc of the Milky Way, the home of the nebulae where massive stars are exploding and producing new generations of stars with wonderful elements. We know that about the Milky Way, but let's see what Andromeda is doing in the meantime. So we're going to zoom in, and let me see if this works. Yes. And I'm going to remove the label again so you can, the darkness of the screen will hopefully let you see detail. Fasten your seat belts. We're going to be zooming in a lot. You'll see the 2 companions of Andromeda. Right there is one of them. But we're going to zoom. We're going to keep zooming till we can see the full extent of the detail that the Hubble Space Telescope is able to see in the Andromeda Galaxy. These are individual stars. This is not an artist. This would be a wonderful Monet painting, but this is not. It's a Hubble image. Maybe it would be a Seurat painting, not a Monet painting. But these individual stars look a lot like that image I showed you of the star field in the Milky Way. We can get the same level of detail now in Andromeda. You can see stars of different colors. You can see star clusters, families of stars like this one, this one. There's been a wonderful citizen science project that's discovered 3 times as many clusters in Andromeda using this image than had previously been known. 200 clusters were known, now 600 are known. And you can see dark patches like this one of clouds of gas and dust in Andromeda. This is another reason to believe that we live in a galaxy that's no different from the Island Nebulae, because with Hubble you can see enough detail that you can see at least the internal structure looks quite similar. And you can do this quantitatively. I'm only showing you pictures. All right. Now, there's another thing that galaxies do. They contain stars, they have exploding stars, they have all of these things. They foster the growth of their chemical recycling plants, very important for us in life. But they also like to collide. They're so big relative to the distance between them that collisions are common. They have intense gravity. So let's look at what a galaxy collision looks like. And for that, I'm going to, again, resort to a combination of computer simulations and actual images of colliding galaxies. The reason I'm going to rely on computer simulations is because it takes too long to follow a single pair of galaxies go through a collision. We'll need some kind of medical miracle to watch that happen. It takes billions of years, okay, for a pair of galaxies to collide. So I may look old, but I haven't seen any pair of galaxies collide, and I bet you haven't either. So what we can do instead is on a computer simulation, we can speed up time. We can take billions of years and turn that into a few seconds. All we have to do is properly simulate the effects of gravity. So I'm going to start this, and I'm going to get rid of the label again. And what you're seeing are two spiral galaxies, and as they approach each other, we're going to stop the computer simulation. Here is a real pair of galaxies that are about to collide. We go back to the computer simulation, and as in a little while, their gravity causes them to start intersecting. As they intersect, we're going to stop the computer simulation right about there. We're going to change our perspective, and here is a real pair of galaxies, a second pair, that are intersecting. We go back to the computer simulation. They start stretching. Each galaxy starts stretching the other one out. We're going to stop the computer simulation. Here's a real third pair of galaxies going through the process. Why do galaxies stretch each other out? If I'm a galaxy and you're a galaxy, I'm going to pull harder on the front row than the back row because gravity is a distance-dependent force. So this tidal effect is what is stretching things out. As the two pieces are about to merge, we stop the computer simulation, change our perspective, and here's a real pair of galaxies going through this process. Now, these are snapshots of different pairs of galaxies at different stages of the process. Finally, when the central parts merge and the black holes of their centers coalesce, we stop the computer simulation, change our perspective, and finally, here's the last pair of galaxies. Now, this is not as remarkable as it might sound. The computer simulation was designed to mimic these particular snapshots. These snapshots are very famous. They're known as the Tumorous sequence of galaxies. Alar and Yuri Tumre did their first computer simulation using a whopping 64 particles. And when they did n-body simulations, they showed that when two galaxies collide, you can get the sort of features that you're seeing today. This was more than a 64-particle simulation that I showed you. Now, you're sitting there and thinking, okay, galaxies collide, and just to give you a quick analogy, galaxy collisions take a long time. So the analogy I'd like to use is the way we study galaxy collisions is no different from how you would study human aging if you were given, say, 1 week to write a term paper on human aging. Human beings don't age that much in a week. So what you would do is put together individuals who are at different stages of the aging process, from newborns to a week old to a month old, etc. And if you put them together, and you put together enough of a sample at each of these time points, you can make some very solid conclusions about what happens to humans as things are going to happen to us. And I'm going to talk about a slightly different discovery. I talked about how we discovered Andromeda is 5 times bigger than previously thought. That was a discovery in 2005 by a group of us led by our Santa Cruz team. In 2012, led by a team out of Baltimore, we used repeat imaging with Hubble to try and measure exactly how Andromeda is moving. Andromeda's one component of velocity, the z component of the velocity, the component along the line of sight, has been known for years, certainly tens of years, 100 years. But the x and y components are very difficult to measure. So Hubble, on the other hand, has super precision. Hubble, by measuring many stars' position once and then again 5 to 7 years later, was able to see these stars shift relative to the background wallpaper of distant galaxies. It's a very subtle measurement, and the equivalent It's like watching human hair grow on the moon. Hubble's precision corresponds to the rate of growth of human hair as observed from the moon. It helps to have a 7-year baseline, but even so, that's the precision with which this was measured. And we said, great, now we can measure x, y. We've already known the z component. So we can predict how Andromeda is going to pass us by. We know our masses. We can predict the trajectory. Components are actually very small. The z component has been known to be towards us. So Andromeda is coming for us. You know, as they say, astronomers wondered why Andromeda was getting bigger and bigger, and then it hit us, you know. So NASA got very excited about all this and put out a little movie. Normally in astronomy, you think about your past. You use a telescope as a time machine to look into the past. They decided to make a movie about the future, Milky Way Andromeda galactic collision. Again, I'm going to remove the label so you can watch what happens in time. Okay, so I'm going to remove this, and I'm going to play the movie. You can see Milky Way, Andromeda is 2.5 million light years away at this point, but in a couple billion years, it's much closer. That's why it looks bigger. In 4 billion years, there's a spectacular collision unfolding between our two galaxies. There is, those two pieces, the main hearts of the two galaxies are still not merged, but by about 7 billion years, they're all, one galaxy. We already have a name for this new galaxy. It's going to be called Milky Way and Andromeda. And honestly, I think we'll stop celebrating Diwali because we'll have cosmic fireworks in the sky every night. We won't have to worry about this. Now, there's something spectacularly wrong with this simulation. Can you tell? Sorry? No, you can. That's a very good point. Are you inside the collision or not? One of the big uncertainties is where is the sun going to end up in Milkomeda? Is it going to be at the very heart? If it is, it's not going to look like this. But, from our vantage point, just like we can see the center of the Milky Way, we would see the center of Milkomeda like this. We could get orphaned from Milkomeda. That would be bad. Not really, not for human life, but, it would look less spectacular. No, the bad thing about the simulation is the mountains haven't weathered in 7 billion years. So I don't know what rocks they're made of, but they're pretty durable. Okay, so we're going to take a step outwards now, go beyond the Milky Way and Andromeda, and I'm going to rely on a movie that one of our colleagues, Shomuk, has worked with Brent. So Brent Tully, a colleague of ours at the University of Hawaii, put together this wonderful montage. It's a documentary taking a bunch of astronomical images. He said, what happens if you fly through the Milky Way? You start with the Orion constellation over there. It looks like a straight line of 3 stars, but the 3 stars are not the same distance from us. So as you get closer, the star in the upper right quickly leaves that nice pattern of 3. You realize the star in the lower left is not a star, it's a nebula, it's the Orion Nebula, and so on. So this is a wonderful image mosaic that represents unrealistic travel. You have to travel faster than the speed of light for all this to happen on this time scale. There's the Horsehead Nebula. And we're going to go past clouds of gas and dust that are nurseries where new stars are born. We're going to go through an exploded star right there. That pink circular object is an exploded star. We're going to fly right through that. This is like a documentary. It's really astronomical images placed at the right distance, and then you simulate this journey. Now, I told you we don't have a long enough selfie stick. We haven't taken a picture of the Milky Way from the outside, but at some point in this movie, miraculously, there's a picture of the Milky Way from the outside. And you'll see that coming up soon. And so I have to put a proper disclaimer here. That part of the movie is not a documentary. You're about to see that. We don't have pictures like this of the Milky Way taken from so far out of the plane. We don't have pictures like this. This is an actor, Shah Rukh Khan, playing the role of the Milky Way. Doing a fine job. We think the Milky Way might look like this from the outside, but these are not, that part is not a real image of the Milky Way. Then you have companions of the Milky Way coming in again, and soon you'll see Andromeda coming in. What is wonderful about this is today, we can, with some great confidence, say that these different galaxies we're seeing, they may look different in shape. They are, some are bigger, some are smaller, but we have a good sense of how many stars and what their masses are. This is the Triangulum galaxy. I'm starting to study this in a lot of detail, just like we have Andromeda. We're going to go through an exploded star there. There's Andromeda with its companions. And in fact, in the left part of the picture, you'll see these sort of what look like grains of salt, especially in the far left there. Each of those little dots is a galaxy like the Milky Way or Andromeda, 100,000 light years across, 100 billion stars. There's a monster galaxy at the center of that Virgo cluster. It's called Messier 87. It's much, much bigger than the Milky Way in size and mass. And this is a daredevil journey, so appropriately we're going to crash into M87. So just give it a few more seconds. You can start to see M87. See if you can spot it at this stage. I'm going to use my laser pointer in a second. I believe it's that. It's a good test. That spot at the center is a dense collection of stars gathered by the supermassive black hole that's at the center of M87. There are massive black holes at the centers of all galaxies. M87 has a particularly monstrous black hole. You can even see this jet emanating to the left. Can you see this jet of blue light emanating from the left? Whoops, whoops, whoops. Wrong button, sorry. Okay, so what we're going to do there is, this is another picture of M87, and we're going to zoom in to the supermassive black hole at the center of M87. Except what happens is, after a little bit of zooming in, we lose resolution power to see detail, so we're going to resort to an artist's rendering of what's going on at the center of M87. It's a very good physicist who didn't find a job as a physicist and became an artist, so it's really informed by physics, even though he or she didn't find a job as a physicist, did a fine job as an artist. So this part is real, this part is a real image, but as we zoom in, I'll get rid of the label again, and you'll see that what we think is going on in the heart is swirling material around a supermassive black hole. There's the jet of material being squirted out. You can see that jet in M87. But if you could look like this, you would see increasingly hot material heated by friction. The white hot, yellow, orange, red represents a gradation in temperature heated by friction. As stuff swirls in, gas heats up through friction. And this is based on a model, a physical model of what black holes, the vicinities look like. Now, as you know, recently, the first image of a black hole was obtained by something called the Event Horizon Telescope. So let me show you a picture of that. This here is the image. What you're seeing really is a silhouette. This swirling disk of gas and dust puts out light in the radio part of the spectrum, and that light from the far end of the black hole is not able to travel in a straight line because the light that's coming in a straight line gets trapped by the black hole. So the only light that can reach us has to travel around the black hole, and in fact is bent by the black hole, by the gravitational lensing of the black hole. So it produces this ring. It's a silhouette. It's taken with what is quite literally the largest array of radio telescopes on Earth. I say it's the largest array of radio telescopes on Earth. That's going to be true as long as I keep the phrase on Earth there, because this used a combination of telescopes scattered throughout the Earth. It used a combination of telescopes, radio telescopes took this image, and one of the beautiful things about this is these lumps that you see at the bottom keep changing because that swirling material is not steady. So the glow is changing, and you can see that in real time. They're also going to image the black hole at the center of the Milky Way, but in terms of combination of distance and mass, this is a very good target. Now, I want to say a few words about work that went on 100 years ago that really sensitized people to these sorts of phenomena. And we need to look no further than one of the most famous physicists of all time, Albert Einstein. There's a picture of him taken in 1912, around the time he was really thinking hard about general relativity and the nature of gravity. The person on the right you may not know as well. His name was Karl Schwarzschild. They both had impressive facial hair, you notice. Anyway, he was a German physicist, and he was the first person to solve the field equations of general relativity in the simplest case of a point mass and spherically symmetric situation. As far as I know, he's the first person to come up with an exact solution. And this notion that if you have a high enough mass concentration, you're going to get a radius around which, within which not even light can escape. So the concept of a black hole is really due to the combined work of these two people. There were other people who contributed, of course, but the event horizon of a black hole is known as the Schwarzschild Radius in recognition of Karl Schwarzschild. Karl Schwarzschild died in his 30s. He was in his 30s. So he did all this work while he was in his late 20s and early 30s. He died in World War I. As a German Jew, he was fighting for Germany in World War I. Sort of ironical. And given what happened in Germany afterwards to German Jews. Anyway, Schwarzschild died in his 30s. It was not, he died on the battlefield. It wasn't gunshot wounds, but it was really because of disease and unsanitary conditions at the battlefront. 1912 was a key year for Karl Schwarzschild because it was the year his son, Martin Schwarzschild, was born. Martin didn't look like this in 1912, but anyway, this is a picture taken much later. I show this picture because Martin was an emeritus professor, retired professor at Princeton when I went to graduate school there, and he was one of my mentors. And one story I remember hearing from him is how, after his father's death, Albert Einstein would visit their home, visit his mother, visit him. He is my 1 degree of separation from Albert Einstein, and I'm your 2nd degree of separation. Okay. So they talked about, Einstein in particular, predicted that light should be bent by gravity, and there's some spectacular confirmations of that. This is a great smiley face lens where the two eyes are big, massive elliptical galaxies in the foreground. Their dark matter is causing light to bend. So these bluish-white galaxies that you see around have been stretched out into arcs by the gravity of the two foreground galaxies. Not only does mass distort space and time in its vicinity, if you have an assembly of mass that's not static but changing, like the spiraling of black holes, you should get gravity waves. These were predicted in 1915. It took 100 years for the first detection of gravity waves to happen. You all heard about this. This was a few years ago. But this was a remarkable moment. The moment when astronomy went from just seeing to also listening. If you can think of gravity waves as vibrations in the fabric of space-time, it's analogous to feeling vibrations. And, the analogy, I love SAT analogies, so let me throw another one at you. What this man is to sports, this result is to all of science. There are people who don't pay any attention to sports, but there are individuals who transform sports for them. This man might be one of them, Muhammad Ali for boxing, Tiger Woods for golf, Roger Federer for tennis. There are individuals who elevate the game to a level where people who are never interested in sports start watching. In the same way, when this result, the LIGO detection of the first gravitational waves from a pair of merging black holes came out, I can tell you for certain many members of my family and friends who don't give a damn about science, who never asked me anything about it, started asking questions about what this was. So I know that this elevated science to a level where people who normally don't pay attention did. Here's a schematic of how this works. You send out a laser beam, and you control the environment of that laser beam very carefully. You split that laser beam so that some of it goes from left to right, some of it bounces and goes up and then back down by bouncing down. And then you look at the destructive interference of these two laser beams. And if you have a perfectly stable system, you can hold it so that the two waves are destructively interfering. That is, you have a situation like this down here, where the wave from one in orange and the wave from the other in red are exactly canceling because the crests and troughs of the two waves are exactly coincident. Now, if you have a slight departure in length, let's say due to a truck driving by one of them, or an earthquake, or a gravitational wave, you're going to get a departure from this. Now, the good thing about trucks driving by is they don't drive by the apparatus in Louisiana and Washington at exactly the same time, and even if they did, they wouldn't produce the exact same pattern. Same thing for earthquakes. So in 2015, I think September of 2015 is when these waves were received. It was a remarkable moment, and I'll show you an aerial view of one of the actual apparatus. Again, 4 kilometers in length. That's where the laser facility is, right there at the center. 4 kilometers in length, aerial view. One of these in Hanford, Washington. One clear across the continent, 3,000 miles away, 5,000 kilometers away in Livingston, Louisiana. And here's the signal that was received. In the upper part, you see the signal received in Hanford, Washington. In the upper left, upper right, you see both the signals received in Washington and Louisiana. And it doesn't take much to see that the patterns are similar to within the noise. And very importantly, the exact chirp, the exact frequency, amplitude signal that was received is consistent with what you would expect from a pair of merging black holes. The bottom two panels are predictions. When two black holes in spiral and merge, what happens is the amplitude of the distortion goes up as the black holes approach each other. They together create a more intense gravitational field. So the amplitude goes up, but the frequency also goes up because they're spinning ever faster. And the reason they're in spiraling is because of energy loss due to gravitational waves. So this was a remarkable moment. Pay attention to the y-axis. You've heard a talk about this, I heard, so I won't belabor this point, but the y-axis, strain, 10 to the negative 21, is a dimensionless quantity. This strain is a physics term. It's not the kind you feel after vigorous exercise, or although you may feel this kind of strain after vigorous exercise, or before an exam. This strain is when you stretch something, and the definition of strain is the change in length divided by the original length. So the 4 kilometer L, each of the arms, oscillated ever so briefly, a fraction of a second. The waves were received at slightly different times in Washington and Louisiana because the source was not directly along the bisector line. Light takes time to travel. It reached one before the other. So light delay time tells you a little bit about where in the sky the event came from. But this was a remarkable moment because measuring 10 to the negative 21 is not easy. It really takes the kind of precision, dedication, effort, practice that characterizes the success of these great sportsmen we talked about. Virat Kohli didn't become a great cricketer overnight. He had to work hard at it, and people who made this discovery had to work hard. Same things, precision, creativity, hard work, persistence. And the oscillation amplitude of the 4 kilometer array was 1/100th the diameter of a proton. A proton is tiny. Okay, an atom is tiny, a molecule is tiny, a proton is already very tiny. 1/100th the diameter of the proton is how much the amplitude of the oscillation corresponded to. Or, in other words, the distance between us and Alpha Centauri oscillated by an amount that's the width of human hair. I love human hair. They come into my analogies all the time. Okay, another thing happened 2 years ago, in 2017. One of my colleagues, Ryan Foley, at the University of California, Santa Cruz, this was not the first detection of gravity waves, but the first detection of gravity waves from a pair of neutron stars. Not from black holes this time, neutron stars. And they saw the accompanying light, and that's pointed to in the grayscale picture. That spot of light wasn't there, but after the gravity wave alert, their images showed this spot of light. Now, what is remarkable about this is through all of human history, human beings have been walking through this fantastically beautiful forest that we think of as our universe. It's a beautiful forest. We can see everything within it. We can see a lot of detail, but we can't hear a thing. It's a beautiful but silent forest. The universe has been, the study of astronomy has been analogous to a walk by the human race through a beautiful but silent forest. In 2015, we heard the forest for the first time. not because the forest had changed, but because our hearing precision had changed. We had the right kind of hearing aid to be able to hear the first chirp, the bird chirping in that forest. The first few chirps were disappointing because there were black holes merging, exciting in some way, but when you turned around to look at that chirp, there was nothing to see. It's this chirp, due to merging neutron stars, that led to an explosion of light, a burst across the energetic spectrum, electromagnetic spectrum, actually, energetic burst across the whole electromagnetic spectrum, detected in gamma rays and light. So this time, you heard the chirp, you turned around, you could see the proverbial bird fly away. This is really important for human history. It's the advent of multi-messenger astronomy. One more thing about bending of light, and then I'll start to wrap this up. I had the privilege of hearing Stephen Hawking speak about life in the universe a few years ago, and this is my little tribute to him. As you know, he passed away not so long ago, and he made a remarkable, he and others worked together to make a remarkable discovery that black holes can actually lose mass from their surface. They can evaporate at a very, very slow rate, but if you bring together special relativity, general relativity, and quantum mechanics, you can put that together and you conclude that black holes should ever so gradually lose energetic particles in the form of radiation from their surface. They should radiate like black holes. All right. So black holes, I'm going to leave them behind, and I'm going to go back to the galaxies I love, and I want to spend just a few minutes talking about where the Milky Way came from, and the answer to this will take us to the earliest imaginable moments in the history of the universe. They take us back to a universe that was governed by quantum mechanics, where fluctuations were, quantum fluctuations were important. And so I'll, whenever you think of quantum fluctuations, quantum uncertainty, here's Schrodinger's cat. You see two versions, a live cat, dead cat. Schrodinger's cat experiment was envisioned by Erwin Schrödinger as an example of how quantum uncertainty is not limited to the microscopic world. It can affect macroscopic things like cats. So that radioactive material has a probability of emitting an alpha particle if you leave that box closed for an hour. So after an hour, there's a 50% chance that a particle would have been emitted, 50% chance not. He sets up a special Geiger counter, so the particle, instead of causing a beep, causes a hammer to fall on a bottle of cyanide that kills the poor cat. It only does that 50% of the time. So the uncertainty in that fission of that radioactive material ultimately translates to uncertainty in the life of the cat. So, again, you either have that or you have that. And you can't predict, if you set up 1,000 boxes, you can only say that 500 of them are going to have live cats when you open the box and 500 won't. You can't predict which ones. Okay? So Schrödinger used this to explain the nature of quantum uncertainty. He was an animal lover. No animals were harmed in the making of this experiment. It's a thought experiment. I have to tell you this Heisenberg incident. Heisenberg, who's really the author of the uncertainty principle, he was once caught speeding on the Autobahn. The German police, traffic police, pulled him over and asked him, "Professor, do you know how fast you were going?" He said, "No, but I know exactly where I was." So if you get it, I feel sorry for you. Okay. So the Schrodinger Cat Experiment was never carried out by Schrödinger, but the universe went ahead and carried out its own version of the Schrodinger Cat Experiment. Because what happened was shortly after the Big Bang, there were fluctuations, quantum fluctuations in the fabric of the universe. There were upward and downward fluctuations in density. And just like the Geiger counter transports that quantum uncertainty into the macroscopic world, inflation, a very rapid period of expansion in the universe's history, took these quantum fluctuations, took them from microscopic to macroscopic. Gravity then took over to produce galaxies. So the Milky Way we live on is a live cat in the universe's version of the Schrodinger Cat Experiment. The voids between galaxies are the dead cats in the universe's version of the Schrodinger Cat Experiment. Now, I talk about quantum fluctuations. We can actually see these in the afterglow from the Big Bang. So these are the early ripples in the cosmic ocean. Let me play this for you. The blackish, black-blue points are lower temperature than average in the afterglow from the Big Bang. The reddish-yellow pieces are hotter than average. If you take these fluctuations, if you start with these very subtle fluctuations, as we will here, and see what happens as you go forward in time, gravity takes these very subtle fluctuations. Gravity, just like human society, makes the rich richer over time, and the poor poorer. So dense regions get even denser. As you can see here, you get the development of something called the cosmic web. And I think it's fair to say that in addition to powerful telescopes, powerful computers have really revolutionized our understanding of things like this in the universe. So this is, you see for scale, that's 500 kiloparsecs. 500 kiloparsecs is 500 multiplied by approximately 3,000 light years. So this is about the scale over which the Milky Way would have formed. You can see time counting up in the upper right. Capital G is billion, so this is less than a billion years after the Big Bang, but as I'm not going to play the whole movie, but you can see that gravity is supposed to have produced galaxies. So in a sense, since we need galaxies for cosmic life to have emerged, and we need quantum fluctuations and inflation and gravity for big galaxies to form, really the origin of life, complex life on Earth, relies on all of these things. You start with quantum fluctuations, inflation, gravity, and then you get the galaxies that can act as chemical recycling plants. So just to wrap up that story, here's the afterglow from the Big Bang. In it somewhere, there's an up fluctuation that's going to lead to first an infant galaxy that's going to cannibalize things around it to produce a big galaxy. Within it, there'll be stars that enrich one another, especially through explosions. Out of these exploded remains, new stars and planets are formed. They have complex molecules and wonderful life forms. Thank you.
Thanks very much, Raja. That was great. And I'm glad you ended up with your son and your daughter in the picture.
Not a sibling rivalry between
we we have time for a few questions, if that's all right.
That's fine with me.
There are microphones all around. Please raise your hand. Maybe we can take a few. Right.
Yes, please.
Shivam already captured somebody by a microphone.
Oh, okay. All right. Okay.
You're out of luck because the microphone takes precedence.
Thanks for the good lecture,
Thank you.
Professor. I would like to know that how could we escape the collision of two galaxies like Milky Way and Andromeda? And if we are to escape the collision or avoid the collision, how can dark energy help us in this process? Because the property of anti-gravity property of which is repelling of two galaxies away from each other.
That's correct. That's correct.
So how can dark matter help us to avoid the collision of two galaxies?
So in the case of the Milky Way and Andromeda, that's a great case where, yes, there's dark energy in the space that the Andromeda and Milky Way galaxy are in. And for those of you who don't know, dark energy is this anti-gravity outward force. There is anti-gravity, but the gravity, in this case, the dark matter, has won over anti-gravity. So there are pockets of the universe where dark matter is dominant over dark energy, and our Milky Way Andromeda case is one such example. So we cannot escape that collision. We don't need to escape that collision. The collision is not going to be bad for us. It's not that stars get, stars don't get ripped apart. Planets don't get ripped apart from stars during galactic collision. Galactic collisions are surprisingly benign. They pass through each other. So, yes, in general, you have dark matter and dark energy. As we live in this double dark universe. I used to say gravity sucks and dark energy is truly repulsive, but we really don't understand their nature, except we do know how much there is, and in the local group, Milky Way Andromeda, dark matter is winning over dark energy. On average, dark energy is winning over dark matter in average parts of the universe, but we live in a denser than average part. Other questions?
Sorry, we think that somebody else asking a question. Can I ask a question now? Okay. So, as far as we know, as you said, that the universe seems to be expanding, and dark energy seems to indicate that it's expanding even faster than we thought. but everything in terms of matter in your universe seems to be contracting. So where's the catch?
Okay, so the catch is, on average, the universe is expanding ever faster, on average. But there are pockets of the universe where the universe is expanding slower than average, and there are pockets where it's expanding faster than average. When you have voids in the universe, those are actually expanding faster than average, and the overdense regions of the universe, like the local group we live in, it's not just expanding slower, the expansion has been reversed and it's contracting. So the statement that the universe is expanding is indeed accurate, but only as an average statement about the large-scale properties of the universe. It does not literally apply to each and every pocket of the universe.
Small scales, gravity wins. I should add to that. The thing is, gravity becomes stronger than the expansion of the universe on the scale of Andromeda and us.
Yes.
And that's why we are colliding. We're not, if the gravity was not there, we would have expanded with the universe.
Hi, here. Yeah, real quick question. Can we look back at time and look at some of the changes in our galaxy and say for certain, or either way, that the Milky Way that we are living in right now is the first ever galaxy, is the original galaxy, or we have had collisions before?
We've had many, many collisions before. The Milky Way galaxy, first of all, we can't look very far back in the Milky Way because of its finite size. The only way we can look back is by looking far. And so the 100,000 light years, that's the diameter of 500,000 light years, 500 million years is about how far back we can look in the Milky Way. That's a small amount compared to the time over which the Milky Way is formed. Yes, the early part of the Milky Way probably formed very shortly after the Big Bang, but it wasn't the galaxy it is today. It's grown bigger by eating smaller galaxies. And we can, in fact, see the undigested remains of its latest snacks even today.
So you showed us a simulation of, colliding galaxies interleaved with some images of, actual galaxies that were colliding, and therefore drew inference that the principles of the simulation seem to find instances in different stages of the simulation. So I had two questions about that. Number one is that because there are so many colliding galaxies, and there may be different initial conditions and different masses, just because you find an example that of a collision that matches your simulation, isn't it too much of a conclusion that the principles of your simulation are correct?
No. So I can answer that first, then you can let you answer the second question. You're absolutely right. That particular simulation was designed to match the parameters of those 5 systems. In particular, it involved 2 equal mass disks. So the relative masses, the relative speeds, the amount of angular momentum, there are lots of variables, and similarly, there's a lot of diversity in the nature of the different colliding galaxy pairs there are. So it's not just that one simulation. People have done many, many, many simulations. They've really explored these parameter spaces. Again, relative masses, shapes, angular momentum, masses of the individual galaxies, their orbital angular momentum, their orbital energy. These are all factors that play a role. It's not as simple as explaining these 5. You're absolutely right. It's far more complex than that. Your second question.
Yeah. As I thought, it would be a very studied thing. So then if there is a degree of confidence in the principles of the simulation being proven right, then the problem of we not being able to see the shape of our own galaxy because we are inside it. As regards that, why won't the following approach be doable? That we know our sun, we know the nearest star after the sun, and so on, arrange them increasingly in order of distance, and study the speed at which the velocity, the speed and direction in which they're going, and let that do that for the whole rank ordering of stars around us. And then the simulation which we seem to have devised with a degree of confidence, you apply that and try to generate a shape of our Milky Way.
You could. One of the problems is it's very difficult to measure all three components of velocity for one thing of the stars. We can measure one of the three components quite easily. The other two components are quite difficult to measure. Secondly, there's a lot of obscuration by dust, so getting a complete census, measuring their true distances, these are challenging things. Practically, they're challenging things. So we have a fairly good sense of what the Milky Way structure is, but there's still lots of uncertainty in all of these three things. Not knowing all three components of the velocity, not knowing positions, not having a complete census. These are issues. It's actually, in some ways, easier to study your neighbor's house. Easier to look out of your window when you're stuck in your own bedroom your whole life and your house has translucent walls, right? It's easier to look out of your window and look at your neighbor's house. You get a better sense.
Thank you.
Guha has changed some of this, but again, obscuration it hasn't completely.
Anyone this side? Anyone actually have a mic? Holding a mic?
Is there another way to detect the dark matter rather than gravity?
Yes, there's a. Let me back up for a second. There's a couple of different ways. When you say other than gravity, motion is one way to detect dark matter. The motion, the speed at which galaxies are spinning, that's one way. Light bending is an independent way.
Also gravity.
Measuring the gravitational potential as probed by X-rays in clusters of galaxies is the third way. There are different ways of probing. In all cases, you're probing the gravitational field. You're using the gravity of dark matter. Now, there are more speculative ways to look for dark matter. If dark matter takes on a particular form where it annihilates, if it's its own antimatter particle, it may produce a glow of gamma rays when there's enough dark matter. These are somewhat more speculative. Dark matter hasn't yet been found in this way. There's also particle experiments to look for what happens when dark matter travels through a detector. These are possibly going to yield fruit in the future, but they haven't yet. So far, it's been gravity that's been the main hook.
I'll take a last question because we have to wind down. Our air conditioning is absolutely failing right now. Who's there?
Considering the multiverse theory, is there any chance that dark matter may be the matter from other universes which are surrounding?
So the question was about multiverse theory and whether the dark matter in our universe could have come from another universe. Look, to be honest, I'm not an expert on this, and something like the multiverse theory is at the boundary where Immanuel Kant found himself 250 years ago. It's at the boundary between philosophy and science. It is literally at that boundary, and I don't mean to say this to demean anything at all, but this is, it's a beautiful theory. It's the next step in the Copernican revolution where our universe is not uni anymore, it's not the only thing, but in order to prove it observationally will take some serious challenge. So answering questions like that, I would say, there are people in this room who are far more expert about this than I am, but it's really stretching what physics was designed to answer. Physics, inherently is something that's based on experimental evidence, and that's really my cop-out to the answer to your excellent question, in attempting to answer your excellent question.
Thanks very much. Let's wind this down. Thanks. Let's thank Raja Thakurta again. Wonderful talk today. And thank you very much, all of you, for coming on a summer evening. I don't know whether anybody has any announcement to make about future talks, but do keep looking at our website to see when our next future talk will be. We were live streamed today on the web. Good. Okay. Thank you. Thanks very much.
can see it. Live streaming was working.